Welcome to Mathmania Academy. In this video, we are going to discuss the Part B questions from linear algebra which were asked in June 2016. The first question is, given a n by n matrix B and we define e to the power b. So, e to the power b we are defining by this fashion. Okay, and it is given that p is a characteristic polynomial of the matrix B. Then we will have to find out what this e to the power p of b. Okay, if p of x if p of x is the it is given that p of x is the characteristic polynomial of b, then by Cayley-Hamilton theorem what happens? Every square matrix satisfies its own characteristic equation. So what we have is p of b is 0. Okay, so we need to find out e of p of b, which is nothing but e to the power 0 matrix. Okay, if you just give it, you just substitute it and expand, what are you going to get? Actually, if you have p of b, then p of b upon 1 factorial plus p of b squared upon 2 factorial, and this is going to be there. Since every other terms are 0, it is an identity matrix. That's it. We move to the next question. In this question, it is given that A is a n by n real symmetric non-singular matrix. Okay, so the entries of the matrix are basically real. It is a symmetric one. Therefore, A transpose is same as that of the A, and non-singular. By non-singular, what can we infer? We can infer the determinant of this matrix is non-zero, and it is given that suppose there exists x in Rn such that this thing is happening. Okay, they are not saying for all x in Rn. If they say for all x in Rn this thing is happening, then we can very well conclude that the matrix A is negative definite. Okay, they are saying there exists x in Rn such that this thing is happening. Okay, in the infinite possibilities in Rn, if for at least if for one x in Rn this thing is happening, then what does it give us? X prime, sorry, x transpose Ax is not going to be positive for all. This thing is not possible. Okay, so this is not possible. This is what we infer from this. Either greater than 0 or greater than or equal to 0 is not possible for all x in Rn. Okay, now with which what are the things that we can conclude? This is what a basic question is. Okay, if it is let me give you some results which may be useful to problems of this kind. If you are given A is a real symmetric matrix, then when we say A is positive definite, if and only if all eigenvalues are positive. A is said to be negative definite if all the eigenvalues are negative. In a similar fashion, you can very well define the positive semi-definite and negative semi-definite, or non-negative definite or non-positive definite. So that will involve, like, if you have to say is positive semi-definite, all the eigenvalues are non-negative. It is either positive or 0. Okay, this way you can very well define. Okay, now let us try to construct examples to discuss the options. For first one, let me take my A to be minus identity matrix. Let us do for simple cases. Minus I2, that is minus 1 0 0 minus 1. Okay, for which if you consider the quadratic form, how do we construct the quadratic form? Simple, x transpose Ax, right? Yeah, so x transpose Ax. So x transpose, let me consider it as x1 x2 and we have the matrix minus 1 0 minus this one and x1 x2. You don't have to check all this stuff, just look at the positions and you can very well write down the quadratic form. So whatever may be the x that you choose from R2, your q of x is what? Negative for all x in R2. Okay, if it is not 0. Okay, for 0 we will get it, this quadratic form is equal to 0, but for all other x we get this one. Okay, but what is the determinant? So here, in order to satisfy the hypothesis of the question, at least for one x this has to be true, but we have plenty of x such that this is true, and determinant of this matrix is 1, which is not negative, so option 1 is discarded. Moving to the option 2, b is equal to minus a, which is positive definite. That is what they are saying. Okay, let me choose a to be equal to 1 0 0 minus 1. In this case, what is my quadratic form? It is x1 square minus x2 square. Okay, my quadratic form is less than 0 for all x in R2 such that my x can be written as 0 comma x2. If I choose x in this way, okay, only the second quadrant is present and the first quadrant is 0, and this x2 can be any value in R, okay, minus z0. In this case, what happens? My quadratic form is giving me the negative value. Okay, here let me choose my b, which is going to be minus 1 0 0 1. Okay, since this is a diagonal matrix, we can very well find the eigenvalues. So eigenvalues of b are minus 1 and 1. You can very well notice that this matrix b is also a real non-singular symmetric matrix. So the definition can be applied. Here we are getting one eigenvalue as positive and the other one as negative, hence it is not positive definite. Okay, then in the third option, there exists y in Rn, and in the fourth option, they are saying for all y in Rn. So that is the main difference between third and fourth option. If we are able to identify one such y, then option 3 is true. If it is happening to be true for all the y in Rn, then option 4 is true. Okay, so we will check it. Okay, let us say in the question it is given that there exists x in Rn such that x transpose Ax is negative, right? So which means we know that A is a real symmetric matrix. If this thing is true, then A must have a negative eigenvalue. Okay, I am saying A must have a negative eigenvalue. I am not talking about the counts. Okay, I am saying at least it will have one negative eigenvalue. Okay, and say it is lambda. Okay, then what happens? A lambda equals lambda x, from which what I can do is that I can very well write this x as, sorry, I have made a mistake. It is Ax equals lambda x. So from this, if I operate A inverse, is it possible? Yes, it is possible since the matrix is non-singular. A inverse Ax equals A inverse lambda x, and this may be written as x equals lambda A inverse x. I can have this way, right? So from this, what is my A inverse x? It is 1 upon lambda times of x. Okay, basically what is this x? Here x is a eigenvector. Eigenvector of what? Eigenvector of A corresponding to lambda, and finally what you are getting is A inverse x equals 1 upon lambda inverse of x. We have said that this lambda is a negative eigenvalue, hence it cannot be 0. So this expression is also valid. So with which what we infer is that 1 upon lambda is a negative eigenvalue of A inverse. So with which what can you say? This thing is holding true. Just go back to the point where we started. So that tells us there exists some y in Rn such that y transpose A inverse y is negative. Okay, this y is what? Eigenvector of A inverse, which corresponds to the eigenvalue 1 upon lambda. So option 3 is true. If we have to check option 4, just consider the matrix 1 0 0 minus 1. Okay, here your A inverse would be the same thing, 1 0 0 minus 1. Okay, so for all y in Rn, that is not happening to be true. Okay, just consider this example, and with which you can very well prove that thing. Moving to the next question, it is given that A is the matrix 1 0 0 minus 1. Okay, and we are given a bilinear map which is defined from R2 cross R2 to R, which is defined in this fashion. Now we'll have to check the correct statement, right? Then, okay, in the first option, they have given that there exists an eigenvector v of A such that AV is perpendicular to V. Okay, so let us examine it. Let V be an eigenvector, all this stuff, whatever is given in it. Let us say it is holding true. Okay, they have said that AV is perpendicular to V. If this is so, then what happens? F of V comma AV is 0. How is it defined? So I am just applying the proper definition of perpendicularity, right? So the inner product of these things are the map of these two has to be equal to 0. So according to the map, this is AV whole transpose and AV which is 0. This is possible only when what? AV is 0. If AV is 0, then what does this mean? This means that this V has to be equal to 0, which is a contradiction. Why? Because initially we have assumed that this V is an eigenvector of A. Eigenvector cannot be a 0 vector. So that is why it leads to a contradiction. Okay, option 1 is false. Okay, in the second thing, what they have given is that this set is a non-zero subspace of R2. Okay, so for let us try it. Okay, the set given is V in R2 such that f of V comma V is set 0. So this one we may write it as V, which takes the form V1 comma V2 in R2 such that what is f of VV? That is V transpose V1 V2, and what is the matrix? That is 1 0 0 minus 1 and V1 V2. Okay, this is equal to 0. If it has to be equal to 0, then what is going to happen? You can very well multiply and see, that is V1 square minus V2 square is 0. So basically this consists of all the elements where V1 is plus or minus V2. We'll have to prove this is a non-zero subspace of R2. Yes, this is a non-zero subset of R2. That is evident. Now to check whether this forms a subspace or not, let me choose U and V in this set. Let me call this set as S. Okay. Then what happens? I'll have to prove alpha U plus V belong to S. This is to prove. Okay. Consider this alpha U plus V. what is alpha? U may be written as u1 plus u2, and v is v1 plus v2. Okay, so this is alpha u1 plus v1 and alpha u2 plus v2. Basically these two things we have taken from S, which means in this my u1 can be uh, like my u1 can be either equal to u2 or u1 can be equal to minus u2. Okay, these things are possible. In a similar way, v1 can be equal to v2 or v1 can be equal to minus v2. This is also possible. If I choose the one way, that's fine. Now let me check. Suppose these are the four possibilities. I In the first one this may be happening, in the second one this may be happening. Okay, I am considering this case. Then what happens? In place of u1 you can replace u2. Okay, so alpha u1 plus v1 is alpha u2, and in place of v1 I'll replace v2, which is not same as that of alpha u1 plus v2. Okay, if I choose the first case in both and second case in both, then they are turning to be equal, but that is not always the case. Okay, whatever may be the thing. Or if I just simply restrict here, okay, I'll change the color and show you guys. If I simply restrict in this stage and proceed, then what do I have? I will have u1 square minus u2 square is 0 and v1 square minus v2 square is 0. This is what I would have just by stating u1 v are members of S. Then I have these things. So alpha u1 plus v1 whole square. This would be alpha square u1 square plus v1 square uh, plus 2 times of alpha u1 v1. Then I have to subtract alpha u2 plus v2 square. This is alpha square v1 square v2 square plus 2 times of alpha v1 v2. Sorry, u2 v2, right? Yeah, u2 v2. Now, so from this actually I am subtracting this quantity from this. So what do I have is that I have alpha square of u1 square minus u2 square plus v1 square minus v2 square plus 2 alpha times of u1 v1 minus u2 v2. So this thing is 0, this thing is 0, but there is no guarantee that this thing is equal to 0. This need not be equal to 0 always. Okay, hence this is not a subspace. So finally our conclusion is this is not a subspace. Option 2 is also false. Moving to the third one, it is given that we are taking two entries from this, and we have f of vv is 0 and f of ww is 0. If this is so, then v has to be a scalar multiple of w. Okay, what is f of vv? That is v1 square minus v2 square. And what is f of ww? That is w1 square minus w2 square. Okay, so this condition has to be satisfied. Let me choose my v to be equal to 2 and 2 and w to be equal to 2 and minus 2. This condition is very well satisfied, but v is not a scalar multiple of w and vice versa. Hence option 3 is also false. Since this is a part B question, we have discarded first three options, since option 4 must be right, but let us check that as well. Okay, what they are saying for every v in R2. So there is no need of fixing v. There exists some non-zero w in R2 such that this thing is happening. Okay, so f of vw is defined in a way that w1 w2. Okay, if you need, it's like I'll change the color. So w1 w2 1 0 0 minus 1 product with v1 v2. So what we will have is that w1 v1 minus w2 v2. Okay, this has to, we must have this has to be equal to 0, right? So when is it possible? This is possible. W1 V1 is same as that of W2 V2. So basically, whatever may be the V that you choose, for every V in R2, there exists some non-zero W in R2. That is what they are saying. So initially, you are choosing your V. You are free to choose your V, right? Then you will have to identify a suitable W such that this thing is happening. Yes, of course, that is possible. If you know what your V is, then choosing W is not a matter. Okay, basically let us assume that I know the value of V. Okay, basically that is happening here. I am free to choose what V is. Okay, then let me choose W1 also in a free way. Okay, I can choose W1 in any way that I want. Okay, let me choose this to be not equal to 0. Then my W2 can be easily found with W1 V1 upon V2. If I just do this calculation, I'll get what my W2 is. Or the other way, if I choose my W2 coordinate, that is based on what V I choose. In my V, one coordinate may be 0, the other coordinate may be 0, that kind of stuff is there, right? So easily we can very well manipulate the value of W1 and W2, hence option 4 is true. Okay. Moving to the next question, it is given that A is a n by m matrix and B is a n by 1 vector with real entries. And we have the equation Ax equals B. When does this X admit a unique solution? This is what we have to check. Okay. Basically, we can treat this matrix A n by m as a mapping from Rm to Rn. Okay. Rank of AB is same as that of rank of A. What? Here they have said that it admits a unique solution. So if it admits a unique solution, then it has to be equal to m. Why so? Think for it, right? So it has to be equal to this thing. So then what? Actually, AXB has a unique solution if and only if nullity of this matrix has to be equal to 0. Okay, this we know, right? In our previous videos also we have discussed this thing. Then if the nullity is 0, then the number of solutions is the cardinality of the field to the power nullity dimension of the kernel, that is the nullity of A. Okay, this thing is happening. So actually, first let us write it down. Then by rank nullity theorem, rank of A plus nullity of A has to be equal to m. So nullity is 0. So this tells us that rank of A is m. Right? So if the rank of A is m, then this has to be smaller than or equals n, because rank of A is what? Smaller than or equals minimum of mn. We have this as equal to m. So n has to be bigger or equal. So that is option 2. Okay. Moving to the next question, we have V is the vector space of all real polynomials of degree less than or equals 10, and T is an operator which differentiate the polynomial that you are considering. Okay, with which we'll have to check which is the right option. Okay, first of all, let me apply T to 1, then it is 0. T to x, I'll get 1. T to x square, I'll get 2x. And T to x cube, I will get 3x square. Similarly, when I proceed to x to the power 10, I would get 10 x to the power 9. So the matrix of T with respect to the given basis would be 0, 0, etc. till 0, 0. Then I would have 1, 0, etc. till 0 0, then it would be 0 2 etc 0 0, and it goes this way, and finally I would have 0 0 10 0. You are able to see that there is only 0 there are only 0 in the diagonal entries. Therefore, trace of this matrix, if we if this is A, trace of A is 0, determinant is also 0, since this is an upper triangular matrix. So the eigenvalues are the diagonal entries. Okay, and all eigenvalues are 0. So option 4, 2 and 1 are discarded. Option 3 is the right one. Yes, you are very well able to see that, like when you find the a square value, then what? So then you would have first two columns 0, then you will have rest of the columns. When you do multiply it for the third time, you would have first three columns 0, then you will have some non-zero column. Okay, a power 4 means you would have 4 zero columns and rest non-zero columns. So like this, when you go for the 10th power, you would have all the entire matrix is a zero matrix. So that we are actually in the question there is m and n such that this is happening. Okay, there is a typo. Okay, option 3 is the right one. Okay, here sorry, I am sorry. So question is right. There is no m and n. We are able to identify some m, that is a power 10 equals 0. Determinant is 0, so that is the right option. Okay, sorry about it. Moving to the last question. Here we have two vectors which are linearly independent. These two vectors are taken from R3. So basically, whatever may be the space that we consider, if we are talking about the linear independence of two vectors, it just meant that they are not scalar multiple of one another. Okay, and here they have defined some delta 1, delta 2 and delta 3, and V is the span of x and y. Okay, so we'll have to check which is that V. Okay, if of course, since V is the span of x and y, of course this x and y are also members of V. In the linear combination alpha x plus beta y, if you choose alpha to be equal to 0 and beta to be equal to 1, then your y is a member. Conversely, x can also prove to be a member. Okay, these two are the linearly independent entries of V. Whatever may be the entry that I choose from V, that will depend on these two things. Okay, so let me choose an entry UVW in V. Then what happens? This x, that is x1, x2, x3 and y1, y2, y3 and this UVW are linearly dependent. If they are linearly dependent, then the determinant of these things UVW x1, x2, x3, y1, y2, y3 is 0. So this is simply u multiplied with x2, y3 minus y2, x3 plus v multiplied with x1, y3 minus y1, x3 plus w multiplied with x1, y2 minus y1, x2, which is 0. So if you just, sorry, actually this is minus, right? Yeah. So if you see, this is your delta 1 value and this is your delta 2 value and this is your delta 3 value. Option 1 is right. So that's it. We'll meet in the next video. Thank you.